Hey guys, thanks for joining. This is the second video in Why Storage Matters for Hyperconverged Systems. I'm Dan Dunham, and I'm your Cisco dedicated DC engineer. So let's jump into it. I'm going to switch over to a smaller head view here, and let's just take a look here. All right, so this first slide is kind of an eye chart. I'm actually going to add a little bit to it here. So really, this is what HyperFlex is all about, and this is really what makes us so performant in the industry. So when you take a look at a HyperFlex system, I talked about SpringPath a lot. Well, that's turned into what we call at Cisco the I/O visor, or you can think of it as a controller VM, or however you want to look at it. So this I/O visor is where all the goodness happens. So let's just take a look at it. The condition of a write. Incoming data comes into the data distribution layer. This layer is really where the meat of it is for HyperFlex. This is where all the magic happens. So when data comes into this distribution layer before it hits disk or cache or anything like that, it is chopped up into 32 meg chunks. Okay, so those 32 meg chunks are then distributed potentially to the local machine caching, but also out to the rest of the machines in the environment, right? So every single one of these machines is used, and the caching in each one of those machines is used as well, right? So this is what makes the speed happen. This is the magic. So as those 32 meg chunks are distributed amongst all the nodes, nothing happens in cache until all those are committed to cache, right? So let's just take a look here. So once every single one of those nodes has committed that chunk write to cache, that's when the acknowledgement comes back to the I/O visor to let the application know that it's free to go ahead and write again, right? So that's when the acknowledgement happens. So depending on whether you're using RF2 or RF3, that's what kind of determines how many of these nodes get a specific chunk of data. And I'll go into that in more detail in another slide. All right, so let's take a look at this. As data comes into the log, the write or the key space on SSD, that key space is a 2 gig space split into two 1 gig spaces, right? So the write comes in and is coalesced into that first 1 gig space. As that fills up, it then flips over to the second 1 gig space. When that happens, that's when it's destaged to the capacity layer. So before it is actually destaged, it is deduplicated and it is compressed, and then it is destaged to the capacity layer. Okay, so at that point, we're in the data persistent capacity layer. This is data persistent as well as this is on SSD. For a write condition, there is no concept of writing to memory or anything like that. It really has to be written to a persistent form of storage media. All right, so that if you had some sort of failure in the system, you wouldn't actually lose data, causing data corruption. All right, so I think that kind of makes sense. So we've talked a little bit about data optimization, inline compression, inline deduplication. Because it's happening as it goes from cache to the final stage or the capacity layer, it's very efficient in how it uses the processor. So it doesn't put a lot of load on the processor. This I/O visor is about 2 to 3% load on the processor. So even at the heaviest loads, it really doesn't put a lot on the processor itself. So, all right, so let's take a look at the read situation, or the read process, if you will. Again, whoops, let's go down one more. So the read process is a little bit different. All right, so in a read cache, as you're pulling data, chunks, remember it's all chunked and it's all striped, and we'll talk about that in the next slide, the details of how that happens. So as that the data is pulled into the cache, it's a 2 gig cache. It resides on SSD, but it also has a memory cache that it can leverage as well. So, so you get a little bit better performance, obviously, when you're using that native memory mode cache. So that's even faster process when you're looking at the read process. We're still pulling data across the network from every single one of these nodes. All right, every single one of these nodes, again, has that cache in it, and we're leveraging that cache as well as the local node as well. So, so it's important to understand this process, because this is, again, this is where the magic happens, right? So there's no other player out there that has this process of writing to or reading from. They don't have this data distribution layer that chunks the data, distributes the data as chunks across the entire environment. All right, so let's take a look at my next slide here. So this is kind of a different way to break it down. This goes into the log structure data layout a little bit, but let's just take a look as data comes in to the system. This is where the chunking happens. So this is a 32 meg chunk. Let's just write, whoops, come on, doesn't want to write. There we go, 32 meg chunk. And so let's take a look at what happens to these 32 meg chunks. All right, so we've got this first 32 meg chunk. It's going to go to the local machine, let's say. It's also going to be replicated across the network out to other machines. We're assuming RF3 on this, right? So we'll just write that up here. We're doing RF3. It's replicated to 3 nodes in the system. All right, so let's change the pen color here if I can, and it's not letting me, so I'll do it manually. So this is the interesting part. So I told you that every single one of these, or all these reads and or writes, use every single node in the system, right? So here's what's going to happen for this second chunk. The second chunk is going to be written here, going to be written to this one, it's going to be written to this one. All right, let's change out to the third. Oh, look at that, I can change my pen. All right, let's take a look at this third chunk. This third chunk is written to this one, and this one, and this one. All right, so you can kind of see here, it's taking a round robin approach to spreading those chunks across the entire environment, so that you don't put a load on maybe the local system or one of the other systems, right? It's balancing that load across the entire network or the entire cluster. So there's really no hot spot. There's no reason to worry about one node consuming more storage than another. The chunks are spread across the entire environment very evenly. All right, so what happens when these chunks are ingested into the system? So the chunks come, well, let's change out my color here again. Let's get this nice maroon color. All right, so as the chunks come in, they are then coalesced into stripe units, right? They're 256 meg stripe units. Those are put together into 2 gig writes to the write cache. That's on SSD, right? So then this whole stripe is destaged at that time. Remember, we had the two sections. One section is being written to while the other one is being destaged, and back and forth and back and forth. All right, so so that is then destaged to permanent disk or the capacity disk, whatever you want to call it. And that's where, right there, is where dedupe and compression happen, right? So it's very, again, it's very processor efficient, if you will. All right, so this is destaged, but it's not just destaged and splattered all over the disk. It is destaged in a single write very efficiently to that disk. And again, this comes back to the log structured distributed file system and how it works on disk. All right, so it's destaged to a stripe. This stripe uses inode technology to really, so let's just put that over here. So your inode is in the stripe, so you're not really writing files per se to the disk. There's no concept of writing files to the disk. It's all a sequential write. So if, let's say, you wrote a file to the disk, and then you overwrote that with some changes, those changes are then appended to that stripe of disk, and then something, that data that's no longer needed is then marked as defunct, right? So because of that, you have to go through a garbage collection process. All right, I'll just abbreviate it that way. So garbage collection happens in the background on the system. It doesn't put a lot of strain on the system. It can happen during evening hours. It can happen during off-peak times, and so on. So as those blocks change, or not change, as those blocks are marked as not needed by either a snapshot or the actual data set itself, garbage collection comes along and marks them as usable, right? So now that block can be used again. Now the other thing that this does is, as it's going through this process, it also coalesces all the actual usable blocks into a single stripe. So it rewrites the data in a single stripe, so it's very efficient in how it's using that disk. Because if you didn't do that, you'd have massive problems with defrag or fragmentation, I should say. So really, they've taken into account fragmentation that can happen with the log structured layouts. If you want a lot more in depth on these, my next slide is going to give you some resources here. So this first one, it's a great video. It's about an hour and a half long, and if you're interested in this stuff, you'll probably be riveted. If you're not, it might be a real slog through that. But it gives you great in-depth information about the SpringPath Halo architecture. Okay, so this is actually when SpringPath, it's probably 4 years old now, but it still holds true because the underlying technology that they developed for this product is still there. I mean, it's part of what Cisco has made or built their product on. All right, so if you want to look a little bit more at log structured file systems, there's some videos here. There's some interesting white papers. This one's kind of an interesting way to present it. This one is probably a little more professional. Reading both might give you the insight that you're looking for. I'd say take a look at these if you're really curious about the log structured distributed file system. It's definitely going to be worth your time. Thanks for watching and have a great day.